So with this presentation, what we're going to do is going to look at some past calculations from previous WACE exams to see how they attacked this concept of the titration. Now, within different exams, you get a varying type of question. So you can go from the simple ones through to the hardest ones, which are what we call back titrations. So let's have a look at this one. This one comes from the 2010 WACE exam, so quite a while ago, but still quite a good question and one that stood the test of time. So they always like to provide some kind of context to these questions, and WACE questions are often very wordy, and that's something that you have to sort of get around in your head, is that they look big, but what we need to do is try and hone in on the important information. So with acids and bases, one of the practical applications of them is in the idea of antacids. So your stomach produces too much acid, hydrochloric acid. When there's too much acid, it bubbles too much, it basically rises in your stomach, goes through the valve at the top of your stomach and into your esophagus, which is not protected by a layer of mucus that can stop the burning and gives you pain. So to reduce that, you take an antacid, which reduces the amount of acid, not all of it, but some of it, in your stomach to reduce the pain symptoms. So what we've got here is a scenario. Milk of magnesia is where magnesium hydroxide is a solid, is suspended in water, so it's a solid, it's not dissolved, it's a solid, it's floating about in the water. An alternative preparation is aluminium hydroxide, that's a different one. If you go and look at something like Mylanta, which is sold in supermarkets, you might find that it's actually a mixture of both of those two insoluble bases. So a student was going to compare the effectiveness of these two antacid preparations, so buy them from a local pharmacy. He titrated both of them against hydrochloric acid to determine how much acid each could neutralize, and then he looked at the active ingredient of each. Now, hydrochloric acid is not a primary standard. It does not meet the criteria for that, so what we need to do is standardize it first. He chose anhydrous sodium carbonate as the primary standard. So for 2 marks, it's a 20-mark question, so that's 200-mark paper that year, so 10% of your marks from this one long question. Did the student select an appropriate primary standard? Explain. So yes might be your answer, because you've learned that anhydrous sodium carbonate is one of the primary standards that you know. Fortunately, saying yes gets you 0 marks, because it's a 50-50 guess really, if you don't put any data or explanation with it. So the explanation is 2 marks. So 2 marks, 2 clear things. Now, there are a number of characteristics of a primary standard that you would need to state. So something like available in high purity, not hygroscopic, highly stable, doesn't react with oxygen, those sorts of things. You could say easily available in large quantities. I don't love that one, and I don't love the one about that's cheap and easily available either. You've got to focus on the reactivity bits. So low hydrophobicity, available in high purity, and also the other one, of course, was high molecular mass is another one you can use. So here we get into the calculation. Alright, so let's look at the numbers we've got. We've got a concentration of a solution right there. We've got a volume, and we've got another volume. Alright. So this is the primary standard reacting with the hydrochloric acid. So first of all, we need to have an equation. So our hydrochloric acid reacts with our primary standard to make, of course, salt plus CO2 plus water. Write down underneath our figures, so 24.35, 25 mils. Now how do I know it's 25 mils and not the litre? So is it this one or is it this one? Alright, so the titration happens with the aliquot. Titer, aliquot, match those two up. So the initial sample, he made a big sample of it. We don't want to keep that one. And we know the concentration of this is 0.248 moles per litre. Okay, so have your data like that. We know that the concentration and volume of the primary standard, so we can do something like that, which is calculate the moles. C times V. So 0.0248. So we know that. Alright, now we must show our mole relationship and show how the hydrochloric acid is related to the primary standard. So, number mole of HCl is 2 on 1, unknown over known. You must show this. 2 on 1 times that number. You can show your numbers as scientific notation if you're happy with that, or if you're more comfortable just using decimal number like that, then please do so. Don't worry about scientific notation. In the old days they were a bit picky about it, but it's not an issue anymore. And then finally we've got our concentration of our hydrochloric acid, which is simply number of moles on our volume. So this is where we need our titration value, which was, and you don't forget to convert it to litres. Now, with significant figures, it's got to be to the lowest number of significant figures as the appropriate answer. So that would be 3 because of a 25 ml alicot. But remember that you only have to show it when you need it. So I would keep the number as accurate as possible. Right, so here's where they're putting some practical components in. Again, they've got the words that can make it a bit confusing. So he's talking about, and you need these information later, talks about suspension was shaken, 20 grams, that's important, was weighed out and transferred to a 250 ml vial flask, and then it was diluted with deionized water and shaken vigorously. 10 mils of the diluted suspension were then transferred for a titration. Now we've got a table that's got our titration results in it. Now this is a really common thing to do in the WACE because it means that you have to do a bit of calculation, but it also means you have to be aware of a concept called Concordant Titrations. When you do your trials, the first one is usually inaccurate. The other 3, and a minimum of 3, need to be within 0.1 mils of each other. That's what's concordant. Sometimes the WACE will slip in the first one as being just a fine titration. It's totally okay because it's not a trial. They don't give you the trial. In this case, what you need to do is you need to calculate what each one is. So 22.62 is the difference between those two numbers, 21.98 between there, 21.92 between there, and 21.92 there. Now you can see that this one here, the 22.62, is nowhere near 0.1 from the other values, so that's non-concordant, so you can't use that. Then what you do is you take the average of the other 3 and put them together, and we get 21.94 mils. That's only worth 1 mark, that's what you get for that. Now when this question was set, it caused a lot of problems because all of a sudden density, what do I need density for? Well, remember density is actually a concentration measurement as well. So it wants the concentration in milligrams per mil. Milligrams per mil was an unfamiliar unit as well. The density in the table is given as grams per mil, so that's another thing to confuse you. So let's see how we can calculate this. Alright, so what do we know? We know the titer value from the previous question. We also know the reaction, very important. Aluminium hydroxide plus 3 HCl Okay, so there's our equation. What do we know? Alright, we know the titer value and we know the concentration of the HCl from part B. Now, if you make a mistake with part B, you can get follow-through marks for that. Alright, so what do we know? We know the number of moles of HCl is C times V. So from part B it was 0.05092 and our titer value was 0.02194, 21.94 mils, which is 0.00117. We're going to keep the value as accurate as possible. Okay, so we do that. Standard step. Number of moles of aluminium hydroxide is our next thing we want to find out. And that's unknown over known, so that's 1 over 3. Make sure you show your 3 steps. So we have our moles of aluminium hydroxide. Okay. Now, this value here, that is in a 10 mil aliquot. Okay. What we need is what is the concentration of the original suspension. So we need to go and look at what the original suspension was. So the first thing we're going to do is go from the aliquot to the full sample. Now, if you remember the question from the previous page, it said that it was a 20 gram sample that was dissolved in water or made up to the mark in a 250 ml vol flask, and 10 ml aliquots were taken. So that means we need to step it up. So to step it up, the number of moles of the aluminium hydroxide in a 250 is the 250 volume over the 10 ml volume times the number of moles of aluminium hydroxide at 10 ml. Okay, that's called a step up. How we got to that was that we know the number of moles is the same in terms of the dilution factor, but the concentration changes. All right, so that means that rather the concentration doesn't change, I should say. All right, so that's 250 on 10 times 3.27. Which takes us up to 9.30 times 10 to the minus 3. So that's the number of moles that's in our bigger sample. So here we have a small sample, and here we have a big sample. So it's going to step it up into the big sample because the moles change. Concentration remains constant. Okay, so we've got that. Now, all of those moles that were in the 20 ml aliquot, so here, came from the 20 gram original suspension. Okay, so that's really important. All right. So what we want is we want concentration in milligrams per mil. So what do we know? We know the density up here of the aluminium hydroxide, so that's here, in grams per mil, and we know the moles down there. So volume, or density, let's start with density. Density is mass on volume. So what is the volume of the 20 mil or 20 gram sample that was originally added? That's what we want to find out. What is the volume of this 20 grams? Because that's how we're going to get the concentration. So what we need to do is rearrange that. So the volume is density times mass. Oops, it's not correct at all, is it? Volume is going to be the mass on top of the density, which is going to be the 20 grams per mil over 1.12 grams per mil. So 20 over 1.82 is 17.8571 mils. So a 20 gram sample of the original antacid has a volume of 17.8571 mils. So what's the mass? The mass of the aluminium hydroxide is number of moles times the molecular mass, which is equal to 9.30 times 10 to the minus 3 times the molecular mass of aluminium hydroxide, 0.72607 grams. Finally, the concentration of AlOH3 is mass on volume. So we want it in milligrams per mil. We're going to change this to milligrams, so that's 726 milligrams over 17.8571 equals 40.7 milligrams per mil. as your final answer. So dealing with density is tricky. So part 2 requires you to look at the other sample that you had, and they've cut a lot out of it and basically said that what you've got is the mass of magnesium hydroxide from that sample was 1.13 grams. Okay, so what do you do with this? Right, so you do the same thing. Volume is mass on density. The mass is the mass of the original sample, 20 grams, so you're assuming that you use the same procedure, divided by the density from the previous question, or page I should say, 18.8679. So for 20 grams of magnesium hydroxide, the volume is different than 20 mils of aluminium hydroxide because the densities are different. Okay, so then what we've got to do is we've got to look at the concentration. So the concentration in milligrams per mil again. It's mass of volume. So that's 1130 over 18.8679, 59.9 milligrams per mil, or per litre, per mil, per milliliter. Okay. So which is best? What's the best antacid? Well, we need to look at comparing the two. So, magnesium hydroxide. What do we know about it? Well, they're saying that your dose will be 10 mils and that the concentration is 59.9 milligrams per mil. So the mass that you would use is, in this case, you can do masses. You're looking at that going, oh, hang on, it's N equals C times V. But that's when you're using moles per litre as your concentration. You're using mass over volume for this. So it's 59.9, and because it's milligrams per mil, we can say it's 10. We don't have to convert our volume this time. So that's 599 milligrams, which is 0.599 grams. So these are mass of our aluminium hydroxide. For our magnesium hydroxide. For our aluminium hydroxide, it would be the volume is the same, but our concentration is different for this one. Concentration of this one was 40.7 milligrams per mil. So mass C times V, 40.7 times 10, 407, 0.407 grams. So you look at that and you go, oh, well, there's more in the magnesium hydroxide, right? And less in the aluminium hydroxide. Yeah, but that's just the mass. That doesn't tell you how effective it is. What we need to do is to figure out, of course, because you can't just compare masses, we need to go moles. All right? So moles of Na of Mg OH2, good old M equals M on little m on big M. So 0.599 over, we've got 58.326. So there's the moles of that one. And to do the same thing for the aluminium hydroxide, so there's our moles of each, and you say, well, again, the magnesium hydroxide is the bigger number, but we've got to look at how much acid would be neutralized. So, for this reaction, the number of moles of hydrochloric acid neutralized would be 2 over 1 times the number of moles of magnesium hydroxide, which is 2 over 1 times 0.0103, which is 0.0206, So we have that. We go and we have a look at the aluminium hydroxide, and so the number of moles of hydrochloric acid that it would neutralise, in this case, is 3/1, because there's 3 hydroxides. So for the 10 ml sample of each one, you can see that this one is 0.206, this one is 0.105, this one here is the more effective of the two. Right, so skip forward a few years to 2014 and you have a very similar titration question. Again, one tried to put some context to a home situation. So rather than antacid, which the previous question had, this one is about cleaning solution. So they're talking about citric acid. So citric acid is the active ingredient in some bathroom and kitchen cleaning solutions, and they do it with titration with sodium hydroxide. Again, this standardization question. The sodium hydroxide first needed to be standardized. To do this, the student dissolved 4 grams of sodium hydroxide pellets in water to give approximately 0.1 mole per litre solution, and you titrate it with a standard hydrochloric acid solution. The average titration volume was 17.45 mils. So why is sodium hydroxide not a primary standard? Well, all you say is that it does not meet the criteria for a primary standard, which would be high molecular mass, available in high purity, not hygroscopic, and stable, etc. So the previous question, you had to say why something could be, and this one you say why it can't be. Okay, so you list those off. By the way, the hydrochloric acid in there is not a primary standard either, but that would be called a secondary standard. So that would have to have been tested against something like the sodium carbonate from the previous question. All right, so that's quite important. So 2 marks there. Okay, so now we're going to look at the calculation part. Now this was only a 15 marker as opposed to 20 marker in that other example. So show the concentration is 0.0916. So they actually give you the answer. And in recent papers, they've done this a few times, giving you the answer so that it's not about you getting the answer right, and they're actually looking at your procedure. So you can actually miss this whole question and keep going on with the rest of it. They're not trying to say to stump you for the whole question. They're just saying, can you do the calculation? So first of all, we've got our number of moles of hydrochloric acid. It told us what the concentration was, and it told us what the titration value was. So this is what came out of the burette. We then show a mole ratio. It's a hydrochloric acid, sodium hydroxide 1, so it's 1:1 ratio. And then we figure out our hydroxide concentration simply by doing N on V. It's a little bit easier than the previous question, but you can see quite clearly where you get 3 marks from. Again, very familiar table. So they're talking about a 10 ml aliquot of the cleaner. They weighed it to find 10.4 grams. The 10 ml aliquot was then diluted to 100 mils in a volumetric flask. Against the standardized sodium hydroxide solution, 20 ml aliquots of the diluted cleaner were titrated. So what's confusing about this is they've used the word aliquot twice. So this is where that diagram sort of approach really helps. So they took a 10 ml sample of the original cleaner. They diluted it to 100. They then took that 100 and took 20 ml samples to do the titration with. And these are the values of the titrations, okay, of the sodium hydroxide titrations. In the previous example, I was telling you about how sometimes the first value we can use and sometimes the first value we have to omit. You can't just assume that the first one is going to be a roughie. Now, usually it would be, but we've got to look at the actual values. So when we look at the values, you can see this is what you get. 21.8, yes, 20.85, 20.9, 20.95. Again, the first one's not usable, is it? 21.80 is 0.95 different from 20.85, so quite different. All right. So what's the average? You can only use this, the number 2, number 3, number 4, and we get 20.9 because they are all concordant with each other. Why is this one 2 marks and the previous one 1 mark? Well, that's a good question. I don't have the answer for. Sometimes certain markers want a number of marks. You know, you might have lost a mark here if you hadn't had the units, for example. You might have the wrong number of significant figures, for example. It varies from year to year. Now this is important. Citric acid is a weak triprotic acid. What's its composition by mass? Okay, so it gives you the formula, but weak triprotic. So, by being triprotic, it has 3 ionizable hydrogens. That means it has to react with 3 sodium hydroxides. So, salt will be Na3C6H5O7. Okay, Na plus. The citric acid will be triprotic, means it loses 3, it will be a 3 negative ion. Got your titration value, got your concentration, so there's your moles. We have to, first of all, calculate the number of moles of citric acid, so that's 1/3 unknown over known. Then you can see we've got the step up, so you're going from your 20 ml aliquot up to your 100. So that step up is always going to be, if you're going from the aliquot to the volumetric flask, it's always the volume of the volumetric flask on top and the volume of the aliquot on the bottom, because we're going from the little sample to the big sample. Now, the big sample, the 100 mils, will have the same number of moles as in the 10 ml original aliquot, the 10 ml sample that we diluted. The moles aren't changed when you dilute, so you can just take those moles and figure out the mass, because I gave it to you there. And then we get the percentage composition like this. The mass of the pure over the mass of the, because I told you it weighed the sample. Now you go 6 marks. How do you get 6 marks there? Right, 1 mark for the equation, 1 mark for the sodium hydroxide, 1 mark for the citric acid originally, 1 mark for the step up, 1 mark for the mass, 1 mark for percentage composition. Right, this next part is asking you about an indicator. So what's the suitable indicator for this titration from the table below? Alright, so it gives you a number of indicators. Which one do you choose? Now there's a couple of ways you could do this. One, you could remember that a strong base and a weak acid titration will give you a certain pH range. So you could try and memorize the equations. So strong acid, strong base, weak acid, strong base, weak acid. You could remember those. But what's better to do is to look at the product of the neutralization equation, which was C6H5O3, it's O7 3 minus, and show it ionizing with water. This is in your explanation, because if you just memorize it, you can't give an explanation. Now, C6H5O7 3 minus will be a proton acceptor. It will take one back and leave a basic conditions behind. So basically that means, essentially that means I should say, that you want basic conditions. So methyl yellow changes in acidic, litmus changes at about pH 7, bromothiamyl blue is similar, thiamyl blue is clearly basic. That is your answer. So what you have to do is justify, choose thiamyl blue, and then show with the use of an equation the answer for that one. So this one was from the 2016 WACE paper, which was the first of the first exams of the current ATAR syllabus, how it's structured at the moment. So this was a really good example of how they merge different concepts together in one question in terms of the different ways we can look at components of a titration question. 26 marks out of 200, so it's pretty hefty, and it was the last question in this paper. So a lot of students found a bit of difficulty getting to this, but also there were lots of components to it. So what we've got is we've got the context setting, and it's important to look at that carefully because it talks about what acid rain is. Gives you some legislation. Obviously, that's irrelevant to the question, but there is a couple of important bits of information in there. It says that normal rain has a pH of about 5.6. Rain with pH less than 4.4 is classified as acid rain. So make sure you circle those two things. Talks about some testing. So the rainwater is acidic, so they've got to titrate that with a base, but the base, of course, is not a primary standard. So you need to standardize the sodium hydroxide against the primary standard, in this case our good old friend sodium carbonate. Sodium carbonate, as we talked about in our primary standards video, was heated to 110 in a drying oven, and then a certain mass was dissolved in water to make 2 litres of the primary standard. Then 3 25 ml aliquots of hydrochloric acid were titrated against that primary standard to make hydrochloric acid the secondary standard. This hydrochloric acid was then used to standardize the sodium hydroxide. So you've got 2 titrations before we've even got to the rainwater. So let's have a look at the calculation. As in the previous example I gave you, they've given you the answer. The reason they gave you the answer is that if you can't do this part of the question, you can still carry on with the rest of the question. But this is about the standardization of the hydrochloric acid. Gives you the answer, 3.76 times 10 to the minus 6 moles per litre. How do you get to that? Well, if you can get to that, you've got some safety in that, and that you can, what you need to do is replicate the steps to get there. If you're not sure, you can make some mistakes and still use that answer later on. So, what do we got to start off with? We know what the mass of the primary standard was. So if we know the mass of the primary standard, we can figure out the moles. Now that's in the 2 litre sample. Alright? The primary standard was placed into the burette. And we know that 16.4 mils came out of the burette. That was the tighter volume. So what's the same between the 2 litre sample and the 16.4 that came out of the burette? Well, the concentration is the same. So we can step down the number of moles. And we do that like this. The number of moles that was used to react with the aliquot is 16.4, which is what came out of the burette, over 2,000 mils, or 2 litres, times the number of moles in total. So we therefore figure out that's what came out of the burette to react with the aliquot. We have a reaction, obviously, sodium carbonate and hydrochloric acid forming salt plus water plus CO2. So therefore you can say that the number of moles of hydrochloric acid that was in the 25 ml aliquot is 2 times the number of moles of sodium carbonate that came out of the burette. We then need to work out the concentration that was in the 25 ml pipetted sample, or the aliquot, and we get 3.76 times 10 to the minus 6, which is our answer to our question. So you can see how we got our 5 marks there, 5 things. Now this question comes up a lot again. This is one of those theory parts, and I've mentioned before that the theory comes into these a lot. 2 reasons why sodium hydroxide is not a suitable primary standard. 2 marks. So this one doesn't ask you yes or no, because as I've told you before, yes or no means nothing. You don't get any marks for that. So they've just asked the reasons why it is not. You could have anything like this. Difficult to obtain in very pure form, readily absorbs moisture, H2O from the air, you can use the word deliquescent, or you can say hygroscopic. Readily absorbs more CO2 from the air, it's another one. That's to do with its reactivity. Mass varies over time, or has a relatively low molar mass, so any of those are acceptable. Just 2 of them, not all 4. No point to overkill it by writing more than 1. By the way, if you're tempted to write more, so that you sort of scattergun approach or write as many things, the examiner's going to take the first 2. So if your first 2 are wrong, but your next 2 are right, you don't get the marks for that. So if it says 2 marks, just write 2 things. Writing 3 things and one of them is wrong, and it's your first one, you only get 1 mark for that. Okay, so now we're getting into the titration bit. An average titer of 21.3 of that standardized hydrochloric acid solution was required to neutralize 25 ml aliquots of our sodium hydroxide solution. So we haven't even got to the rainwater yet. Only 3 marks. So we know what came out of our burette, concentration times volume. Mole ratio. In the year this exam was run, lots of students got 2 marks because they didn't state this very simple mole ratio. They went straight from the number of moles of hydrochloric acid to the next part of the question and didn't make this statement, so you don't get the marks. You have to do that. And then the concentration of sodium hydroxide is simply mass, number of moles on volume. So 3 marks, quite simple for that. Back to our theory. So what are we going to wash the glassware with? It says, carefully before we get to the rest of it, 100 ml sample of rainwater was collected near the power station, diluted to 250 with distilled water in a vol flask, and 25 aliquots were used in the titration. So what do we wash with? Now a lot of students got 1 mark out of 3 for this. Burette, clearly sodium hydroxide. That's the mark. Conical flask is distilled water. Not water. Water gets you 0. It's got to be distilled water. And what went into the pipette? It's the diluted rainwater. Not the original rainwater, because that's of a higher concentration. Got to be diluted rainwater. Once again, the old table business. Alright, so you've got to make sure that these values are concordant. And you can see that trial 1 is way off. It's not 0.1 from the others. So you discard number 1 straight away. So whatever that is, you've got to go and put a great big line through that one. We do not want that one. So what comes next? Get the other three values and add them together and divide them by 3. And our titer value is going to be, of course, 19.66 mils. Now we're getting into the actual crux of the question. What is the pH of that rainwater sample, and is it acid rain or not? So we've got our sodium hydroxide. We now know what the concentration of that is. We don't need the hydrochloric acid concentration anymore. We don't need the sodium carbonate concentration. We need the sodium hydroxide to go from here. So we know that 19.66 mils came out. We previously determined the concentration of that sodium hydroxide solution, so there's the moles. We assume that it's a 1-to-1 ratio by the neutralization of simple neutralization reaction. H plus OH makes OH 2H2O. Sorry, I'll say that again. H plus OH makes H2O. Now, we've got to step it up. Go from the conical flask to the 250 millivol flask, because the moles are different, but the concentration is identical. So we go 250 over 25. Be careful of that 25, because a lot of people, we're used to doing 20 mil titrations in the class. We're going 25 to 250 over 25. Now we go up, so more moles, which is what you'd expect. Now that moles was exactly the same number of moles as in the original undiluted sample, because all you did was add water. The moles didn't change. So the concentration of the original undiluted sample is the number of moles in the 250 millivol flask over the new volume, which was the undiluted volume of 100 mils. There's our moles. From concentration, we can calculate the pH. The pH is 5.2. Is it acid rain or not? Well, to find that out, you've got to go back to part or the actual question. It said acid rain was less than 4.4. This is greater than 4.4, so the rain is not acidic in this particular case. Part G, another 6 marks. Bit of a tricky one, this one. Carbon dioxide is always in rainwater. It's as the rain falls from the sky, it absorbs CO2. And that means that normal rain has a pH of about 5.6. How much sulfur dioxide at that temperature and pressure would you need to produce 100 mils, basically, of an acid rain sample with a pH of 4? And use the equation below. And we're assuming complete ionization of that sulfurous acid, which means it's got 2 hydrogens per acid molecule. So what do? Well, first of all, we've got to look at the difference. We want to know how much SO2 we need to dissolve. So we start off and we look at, alright, a pH 4, what's the concentration of hydrogen ions? 0.0001. And what's the moles there? Well, it's concentration times volume in the 100 ml sample, 1 times 10 to the minus 5. What about at that pH of 5.6? So what was it initially? 5.6. There's the concentration of hydrogen ions, and there's the moles. So what we've got is before the sulfur dioxide is added is the pH 5.6. After the sulfur dioxide is added is 4. So the difference between the two is attributable purely to the sulfur dioxide addition. So we've got to work that out. So the difference in hydrogen ions is the number of moles at 4 minus the number of moles at 5.6. And we get 9.75 times 10 to the minus 6. Now that hydrogen ions comes directly from the SO2 addition. How much SO2 is there? Well, we've got to work out the number of moles of SO2, and it's important to remember that sulfur dioxide is 1/2 the number of moles of hydrogen ions, because each sulfurous acid has 2 hydrogen ions involved in it. So there's our answer for the number of moles, and we just do V is nRT on P, and it comes to be 1.2 times 10 to the minus 4 litres. So there is 3 WACE examples how we've worked through titration questions. You can see that they're multiple component. They're also hefty in terms of marks. There are only 2 types of calculations, really significant calculations in the WACE exams: empirical formula and titrations. So good luck with the rest of your practice, and let me know if you need any help.